have Hongbao Zhang telling us about Petrov type 1 spacetime and hydrodynamics.
Okay, thanks to the organizers to give me this opportunity to introduce our recent work on the Petrov type 1 spacetime and the hydrodynamics. This is my outline, and actually in this work we focus on the random hydrodynamics. It is a fluid due to random spacetime, and from Petrov type 1 condition we can deduce both the Navier-Stokes equations and the relativistic fluid. Actually, we know that in the fluid gravity correspondence, we can calculate the stress tensor, and the coefficients are calculated holographically from the gravity. This is a long calculation, but our question is, since the fluids only have the ambient density, pressure, and the velocity, so from the holographic calculation, can we fix the higher order, first order, and second order coefficients from the background fluid directly? Actually, the Petrov type 1 condition can provide such a kind of relation. Once we give the background stress tensor of the fluid, the first order and the second order terms can be deduced, and the transport coefficient is just exactly meets with the results calculated from the gravity. Okay, then what is fluid and gravity dualities? Actually, in 1970s, people have found that if we disturb the black holes, it responds like a viscous fluid. Actually, even this is draw much attention to astrophysics, because even in Newton gravity, we know that a ball and a sphere shell can expect the same gravitational field to an outside observer. In Einstein gravity, the situation is similar. We only need to using an auxiliary jet function across the sphere shell, and for example, the black hole or the gravity inside the sphere can interact with the matter outside through the Brownian stress tensor on the hypersurface. Of course, such kind of fluid is a kind of imaginary. It is just an duality. We can think that the hypersurface, the gravity inside the hypersurface behavior like a low-dimensional fluid, and so that the fluid equations should satisfy the Einstein constraint equations. For example, it has already generalized to the ADS gravity such that the fluid equations behavior like this equation similar to the Navier-Stokes equations. Okay, so along with the development of ADS CFT, the conformal fluid on the ADS boundary also draw much attention, because in the long wavelengths and the low frequency limit, we can use the fluid to describe the CFT effectively. Especially the higher order fluid can be extracted through, for example, the derivative expansion order by order, and this result was also obtained in 2008, and we can see that this is a shear tensor, and this term just provides the shear viscosities. In natural fluid, the shear viscosity is arbitrary, but such kind of fluid, the shear viscosity is fixed by the gravity. So we can see that the gravity is a special kind of fluid with fixed shear viscosity, and also after other calculation, we can show that they have some special properties. For example, the eta over s is 1 over 1 over 4 pi, and in the membrane paradigm, they also got similar results. So there should exist the relation between the horizon fluid and the boundary fluid. Then a cutoff surface was introduced to building up the relation, and some universal properties have been found. For example, the eta over S and other anomaly properties. We also find that the anomaly coefficients also satisfy some universal relations even on the cutoff surface. So actually, the cutoff not only was used to relate the RG flow properties of the coefficients. If we introduce the boundary condition, we only need to solve the gravity equations between the horizon and the cutoff surface, so that we do not need to desire the spacetime outside of the cutoff. It can either be asymptotically ADS flat or even the theta. So this is give can generalize fluid gravity dualities away from the asymptotically ADS spacetime, because there should exist a universal filter between the gravity and the matter systems. One meaningful development is the Rendler hydrodynamics. We know that for an accelerated observer, there is undue effects. So the Rendler hydrodynamics might also be detected by an accelerated observer. Of course, it also be constrained by the Einstein equations. The constraint equations give the conservation of the stress tensor, and in the non-relativistic limit, it will just reduce to the incomprehensible Navier-Stokes equations. Using this extension and impose boundary conditions, that is the Dirichlet boundary on the cutoff and the regular boundary condition on the horizon, this metric has already been generalized to arbitrary orders, and the terms has been given to the fourth order in this paper actually. And the dual stress tensor is just the Brown-Young stress tensor on the cutoff surface. It can be identified as the stress tensor of the fluid, and the coefficients can also be extracted from such a kind of stress tensor. Especially, and the Hamilton constraint gives the relation of the stress tensor. It is behavior as the equation of state, just relating the pressure and the energy density of the three fluids. And again, the momentum constraint gives the conservation of the stress tensor. It will just reduce to the Navier-Stokes equations. Of course, in higher orders, there is some corrections, but this is higher order correction. We can see that such calculation is a little complicated, and it is actually a long calculation from the gravity setup to the dual fluid. You should calculate the source terms and through integration to and using boundary conditions to determine the integrate constant. So question is, if we only give the find out the background, the pressure and the energy density, can we generate the higher order fluids directly without having the long calculation? So the Petrov type 1 condition was just proposed to reach this aim. It was proposed in this paper that you want to impose Petrov type 1 condition on the p+1 dimensional time-lag hypersurface. Of course, this is also embedded in the Rendler surface. It will give the constraints to the stress tensor. For example, if p equals 3, just in 3+1 dimension, an arbitrary stress tensor have 10 degrees of freedom, and the Petrov condition will impose 5 constraints. So it reduces the totally 10 degrees of freedom into only 5 degrees. So the left 5 it just can be expressed as for example, the energy density, pressure, and the 3 velocity. This is just is the freedom of the stress tensor of the fluid. know that without the condition, the thread tensor is actually arbitrary, and this condition just reduce additional freedom into a fluidity formula. To set up a Newman-Peron-Slack vectors are chosen, and L and K are just the null vectors, and the M are just the special vectors. Actually, Petrov type 1 was first only defined in the 4-dimensional space, and M and the M's are complex vectors. While it was generalized to higher dimension in such a kind of formula. So in higher dimension, it was defined that a space-time is called Petrov type 1 if such a kind of terms vanish. This is just C is the wire tensor of the whole space-time, and this is the Newman-Peron vectors. So such a kind of combination of if such a kind of combination of wire tensor vanishes, we say that the space-time is Petrov type 1. And but it is not the main topic. We only need to using these constraints. So in the original paper, the Newman-Peron vectors was chosen like this, and the special vectors is just the ordinary x, y, z direction, and the two null vectors is just a combination between the time and the normal vector of the hypersurface. As our fluid is only live on the hypersurface, so we only interested in the constraint on the hypersurface. We can using the projections, for example, some Gauss-Cournot equations to project the wire tensor on the hypersurface, so that that constraint can be described using the external curvature of the thread tensor, and our dual fluid is just expressed as the Brownian thread tensor with such a kind of formula. So after some calculation, that condition can just be expressed within the Brownian thread tensor. This condition is just the project on the hypersurface. So actually currently we do not have the thread tensors, and we assume the Brownian thread tensor is arbitrary, and we expand its independent components order by order in the non-relativistic expansion, and we just put the expansion into the constraint we have got. We have said the Hamiltonian constraint is the relation between the thread tensors, just like the equation of state. And the Petrov condition is an additional constraint. We just put the thread tensor into the constraints, and also expand the constraint order by order in this expansion. So at this order, if we demount the Hamiltonian constraint and the Petrov type 1 constraint firstly, we can get the second order of a thread tensor in terms of the lower order, and also express the ij components of the thread tensor in terms of the tau I components. So then currently the arbitrary only left the tau I components, also the trace. The trace we have set it to 0 to choose the gauge, and if we identify this components as the velocity, just using the two equations we got, we can recover the fluid thread tensor up to the third order. Actually, we can compare this thread tensor with the one we got from the from the gravity expansion. It matches very well. And the thread tensor conservation equation just gives the incomprehensible Navier-Stokes. So we can see that this procedure can only using several pages to reach the result. Well, if we perturb the gravity directly, we will need a long calculation. But the question is every space-time with perturbation satisfies the Petrov type 1 constraint? So we should it's better to using some known solutions to track the condition further. We just put the solution have got up to the higher orders, put the gravity solution or thread tensor into the Petrov condition, and also expand it order by order. And we find that the lower orders are just the background order, and the first the order gives the shear viscosity order vanishes identically. But sadly, the next high orders it has additional terms. So it implies that the condition valid at this order. If we still impose the condition firstly, we will also get a stress tensor, but it will does not match with the one we got from gravity. But fortunately, we also find that if we slightly change the original basis, just along with the velocity, we find that only one term left. Previous is additional 3 terms. Actually, this contains the velocity. So we just choose the frame boosted along the fluid velocity. Only this term left, but it still doesn't vanishes. Well, fortunately, this term is we can see that this term is of third order in derivative expansion, and the other 3 terms is only first order or second order in derivative expansion. Then these results motivate us to study the relativistic fluid directly, because that fluid is the expansion in the derivative expansion is expanded in the derivative expansion. Yeah, so the abstraction of the Petrov type 1 condition found in the non-relativistic expansion is third order in derivatives. But the fact that the relativistic expansion presents this condition to second order is expected. Also, the fluids due to Rendeler space using the relativist fluid due to Rendeler space is also well studied. The metric is behavior like this, and if we employing the constraint equations as well as solve the metric stress tensor. This one is just the shear tensor, and this is the verticity. And we can find that the metric solves Einstein equations up to the second order. The constraint equation is just the generalized Navier-Stokes equations, and here is some higher order corrections. And the stress tensor has also been given. Also, we mentioned that the Rendeler fluid has a special properties that its equivalent energy density is there. So when one chooses the gauge, actually one do not appropriate to choose the Landau frame, but the velocity can also be defined slightly. Then this is just a general stress tensor construct generally, and the gravity calculation gives exactly the holographic coefficients. That means the general fluid the coefficients can be arbitrary, but this coefficient is determined by a special fluid due to gravity. Well, in this case, our Petrov condition has become in the covariant form, and firstly, we check the condition using the known stress tensor. We put the stress tensor into the above condition, and we find that luckily it vanishes at the first and second order in derivative expansion. At the third order, we haven't checked because the solution is very complicated. Yeah. Well, this is just a check, and the next step is just it says that if we impose the Petrov condition firstly and only give the background the energy density, the pressure, and the fluid of the stress tensor, can we generate the first and second order coefficients and the tensor directly? Yes, the answer is yes. we have shown that the condition is independent of the gauge choice. So we can define a velocity through such a kind of convention and choose the gauge of the pressure. Then the stress tensor can be expanded along the velocity and perpendicular to the velocity. And for the stress tensor in the constraints we have obtained, the Hamilton constraint and the Petrov type 1 constraint. This is just the start point of our derivation. Then we expand the arbitrary stress tensor order by order and impose the Hamilton constraint and the Petrov type 1 constraint also order by order. Then the first order term can be extracted, and the second order terms can also be extracted. And using some identities, we can recover such a kind of fluid up to second order. And this is just the one we got from the holographic calculation. And if we compare with the general fluid, we can read out the first order and second order coefficients exactly. Well, as I have said, but it is currently not clear whether this condition is satisfied to higher orders because we haven't done the calculation. And but it is possible because the necessary condition for this is to happen is if they exceed an appropriate basis to include the higher order corrections to vanish at this order. Just a short conclusion. We also have shown that we have noticed that we only need the condition on the hyperbolic surface, but actually we have also shown that if we choose the appropriate basis, the whole spacetime with to second order derivation is also Petrov type 1 up to second order. And if we include the Gauss-Bonnet corrections, we know that in ADS gravity, if we the Gauss-Bonnet corrections gives the modification of the shear viscosity, but in the renal fluid, it has no contribution to the first order, but it modifies the second order coefficients. This work is done in this paper. Although the stress tensor is modified by the Gauss-Bonnet coefficients, we also checked that this one still satisfies the Petrov conditions. So this stress tensor can also be derived using imposing the condition firstly. But sadly, in the ADS case, it varies at the first order, just the shear viscosity order. So it means that we cannot able to impose it directly to extract the shear viscosity. But we are also trying to find such a kind of relation, for example, to relate the higher order terms to lower order ones, because it can provide a constraint from the holography and give a much simpler method to calculate the stress tensor directly. So our conclusion is simple, that renal fluid is special. It is much more special than the ADS fluid, and also renal holography maybe have some special properties to study. Okay, thank you. That's all.
Any questions? Okay, is there any physical reason you would expect the Petrov, your generalization of the 4D Petrov condition to apply? You have a generic.
Yes, physical reason, because we can count the degrees of freedom, and so as we said, the gravity holographic can provide a duality to the fluid, but it should also give some new constraints to the fluid. If the Petrov type 1 condition can really be generalized to other kind of fluids, so when we study the fluid, we can use the constraint directly without using the holographic calculation. So it might be provide some new constraints of the fluid dynamics and give some simple expansion to higher orders to to give, for example, the evolution of the equation of motions. Yeah.
If not the same.